Hey, mathletes, here we are looking at similarity in right triangles. So we want to be able to identify similar right triangles and be able to calculate a geometric mean in this unit. One of the first things that we'll need to make sure we can do is identify a hypotenuse of a right triangle. So when we have a right triangle, look for your right angle and draw an arrow across from that. So opposite of that right angle is always going to be our hypotenuse. That is going to be the longest side of our right triangle. Notice the other two sides of our triangles are called legs. For this unit, that's all we really need to know, but next unit we will be talking about trying to decipher the difference between different legs, and we usually do that based off of an angle that we're talking to or in respect to that angle. So an angle here being theta, that leg that is next to, we call the adjacent leg, and the leg that is across from that angle, okay, is our opposite leg. Okay, so what's a geometric mean? So geometric mean of two numbers, a and b, is the length of one side of a square whose area is equal to the area of the rectangle with side lengths a and b. So look at this example. We have a rectangle, side lengths 2 and 8. So 2 times 8, we get an area of 36 for that rectangle. The geometric mean says what number multiplied together will be equal to 36, because we want an area of a square that's equal to 36. Well, to find that, we take the square root of 36 and we get 6. And so 6 and 6 is 36. So a quick way of knowing our formulas is going to be these over here, a geometric mean. Okay, so notice as we set up our proportions, okay, a geometric mean, we will see a variable that is opposite that is the same. So that when we multiply those together, we get x squared. And then this cross, a times b, okay, we get a times b. Notice if we want to solve this, we take the square root of this and the square root of this, and that cancels out our squared here, so then we just have the square root of AB on the right side and x on the left side. So that will be a quick way to find the geometric mean of two numbers. So again, think of our example over here. We just did 2 times 18 divided by, or take the square root of that, square root of 36, and we get 6 as our geometric mean. Okay, which would be the side length of a square that would have that same area, because 6 times 6 is 36. Okay, so when we're talking about right triangles, we need to talk about this line segment here. This line segment here is called our altitude. So the altitude is perpendicular to our hypotenuse, so it's a right angle, okay, and it's a line. That perpendicular line has to go through the opposite angle, or the right angle of the larger triangle. Okay, so what happens here is we get three similar triangles, because if you think about it, the right triangle, okay, we have complementary angles. So we have 3 right triangles here. So I'm going to number these angles. This is angle 1, this is angle 2, okay? And because of similarity in right triangles, if this is a right angle here, then this forces this angle to be 2 as well. And if this is a right angle here, this is angle 2, that forces this angle to be angle 1 here, because we know that angles 2 and 1 need to be supplementary, and we can see that there, that angles 2 and 1 would be the same as a 90-degree angle, or complementary. Okay, so these 3 triangles that we're going to draw here, the first one is going to be this triangle here. So when I redraw my triangles, I like to make sure everything is oriented the same way. So when I orient this red triangle, I'm going to draw it here. Okay, it's the smaller of the 3. Okay, my right angle is here. I'm going to draw my triangles so angle 1 is there and angle 2 is there. And I'm going to label my vertices. So what is my right angle of that red triangle? Well, that's W. What angle vertice has angle 1? Well, this is R. And angle 2 is up here in S. So that's one triangle. So a triangle that is similar to that is also this next larger one. Okay, this triangle here. So I'm going to rotate and flip it and redraw it, and I get a next larger triangle. So I like to kind of put them slightly larger. So again, oriented the same way. So right angle, angle 1, and angle 2. Okay, so for the green triangle, the right angle is W. Angle 1 is up here, so that vertex is S. And for angle 2, that vertex there is T. Okay, so those two triangles are similar. Our third triangle that's similar, and they're similar by angle-angle similarity. We want to talk about a proof or a theorem that proves those similar, because they got similar angles, or congruent angles. So our large right triangle there, okay, our original one before we drew our altitude. So that was always the largest, so I kind of draw that third and draw it slightly larger than the other one, so I have some ideas of what triangle I'm talking about. So the right angle for that is S up here. Angle 1 for that, so again I'm orienting in the same way as I did before. Angle 1 is R, okay, and angle 2 is T. Okay, so now if I want to complete these statements on the bottom, okay, I look for, and I try and set up my rows and columns for my proportions. Okay, so when I look at RW, okay, so RW is over here, okay, and RS, those are both segments, RW and RS, that are dealing with my red triangle. Okay, so then I look at these three redrawn triangles here and I identify them. So I'm just going to identify the sides down here. Those are our bottoms. Okay, and I'm going to call these over here our sides. And then we know that these are our hypotenuses. Okay, so as we're setting up similarity proportions, we got to make sure things line up. So on the left side, this ratio RW over RS is from our right triangle. Well, what are those side lengths? So RW is the bottom of that redrawn right triangle. Okay, and RS is our hypotenuse. Okay, so now to complete this, I look for where is RT? Where is RT a hypotenuse? Well, RT is a hypotenuse in my blue triangle. See, RT is my hypotenuse. So to complete this out, I just need to look for what is the bottom of my blue triangle. Well, bottom of my blue triangle is SR. Okay, notice we have a geometric mean here because these two values, SR and RS, are the same and they're congruent because of our reflexive property. Okay, so let's do this again. So I look for this triangle of the side that I know, okay, or the two that I know. So WS and RW. So WS and RW is coming from my red triangle, okay, and so WS is my side of the red triangle, RW is the bottom, okay. So to complete this out, I'm going to say what triangle has the side, so I'm talking about these sides, that is WS, okay, or I'm sorry, TW. So that is our green triangle. It's TW with that side. So what is the bottom length of TW? Well, that's WS. Okay, and again, notice we have our geometric mean here because WS is WS. Okay, for our third proportion here, again, I'm looking at WT and TS. So WT and TS are both side segments of our green triangle. So WT is our side. Okay. PS is our hypotenuse. So to complete this out, I search for which of my three triangles has a side length of TS. Well, I can see that over here. So TS, this is my blue triangle. So to line up all my rows and columns of my proportion, what is my blue triangle's hypotenuse? And that is TR. Again, we see our geometric mean there. Okay, so these can be shortened down into some theorems. So what we just talked about is the altitude of the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and each other. So we just explored that. Okay, so our first theorem here, these are just kind of shortcuts. You can always just redraw all three of your triangles to do so, but this is our shortcut. We call it the heartbeat theorem. Okay, so it's called the heartbeat theorem because we want to draw these proportions out. So if we do the length of the altitude of the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. So we're relating CD to our segments AD and DB. So we call it heartbeat because you kind of think of it as if you're watching a heartbeat on an EKG, you kind of have this going across. So AD, you jump up, boom, DC, you come back down, DC, and you go across, DB. Okay, so if that helps identify your heartbeat theorem, that's one way to think of it. So notice you have your geometric mean here, DC times DC. Okay, but that's our theorem one, the heartbeat theorem. Okay, the second theorem, we call it the hockey stick theorem. Okay, it's the altitude to the hypotenuse of the right triangle. It separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the adjacent hypotenuse segment and the length of a hypotenuse. So we can see this in two different ways with this triangle. Okay, the first way is looking at it and saying that we have our hockey stick theorem. So we have CB over BA. So if you ever know a hockey stick, you have a short kind of end to it and then the longer side. Okay, so that is CB over BA. Okay, and that's going to be equal to the other hockey stick, which is DB. I wanted DB over BC. And notice we see our geometric mean here of CB over CB. Okay, we can also see that hockey stick theorem this way, and so we get a CA. Sorry, I wanted to look back there. Look at a second hockey stick theorem. So we have CA over AB or BA. Okay, and then the other hockey stick, so then that's going to be DA over AC. And I did write them the different way, but again, you can identify your geometric mean there because AC is the same thing as DC. Okay, so first, let's look at finding geometric means. So if I want to find the geometric mean here, I can think of this as x over 3 equals 12 over x. Okay, so as I simplify this out, I get x squared equals 36. I square root both sides, and I get x is equal to 6. Okay, so now of 4 and 14. So I set my x's in opposite locations, so when I cross multiply, I get x squared equals 56. I square root both sides. I get x is equal to 7.48. Should take these out. There's more decimals, but we should take it out to at least 2 decimal places. Okay, so now solve for x and y. So here I'm going to use my heartbeat theorem. I'm going to say that if I do 2 over 6 is equal to 6 over x. Okay, when I cross multiply, I'm going to get 2x equals 36. Divide by 2, divide by 2, and I get x is equal to 18. Okay, so now that x is equal to 18, notice I do know my entire AB side is 2 plus 18, so that's 20. Okay, so on this one, I'm going to use, for y now, I'm going to use my hockey stick theorem. Okay, and I'm going to say that y over AD, or BA, so y over 20, okay, equals 18 over y. So I'm going to solve it up here, so I get y squared by multiplying this cross. 20 times 18 is 360. Taking the square root of both sides to get y equals the square root of 360. Using a calculator, I get 18.97 for y out to 2 decimal places. Okay. Last example here. So looking at a golf course, Maria drove her ball 192 yards straight towards the cup. So we see that Maria, they both drove from the star. So Maria straight towards the cup, 192 yards. Gabriel drove his ball straight 240 yards, but not towards the cup. So Gabriel ended up here. Okay. We want to find x and y, which is the remaining distance to the cup for both golfers. Okay, so for me, I'm gonna kind of reorient it so it's a little bit easier to see. Okay, and I'm gonna think about how I can utilize these. So the big thing I notice looking here is I don't have the altitude length. If I don't have the altitude length, then I know I need to be using the hockey stick theorem. Okay, so the first theorem I'm going to use is to solve for x. So to solve for x, I'm going to use this hockey stick. So I have 240 over this length. Well, this length right now is given by 192 plus x. So I have 240 over 192 plus x. And then I have 192 over 240. Okay, so now if I cross multiply 240 times 240, I get that equal to 57,600 equals to 192 times the quantity 192 plus x. Okay, so as I distribute my 192, I got to multiply both terms by 192. I get 3,000 or 36,864 plus 192x equals 57,600. Okay, so there's my x I'm trying to solve for, so I'm going to subtract this to both sides. I'm going to be left with 192x equals 20,736. Okay, when I divide both sides by 192, I get x is equal to 108 yards. Okay, so Maria still has 108 yards to get to the cup. Well, that helps to tell us this entire length now, okay, is 300 yards. So that was the distance from the that they had to drive to get to the cup. Okay, so the total was 300 yards. Well, we still need to figure out where Gabriel is. So for that one, we're going to use this second hockey stick. So I'm going to do y over this entire length. So now I know what that x is. So I get y over 300 equals this hockey stick, 108 over y. Notice our geometric mean. So I do y times y, hit y squared, equals 300 times 108, and I get 32,400. Square root both sides, so y equals the square root of 32,400. So y is equal to 180 yards. So you kind of see the importance here of playing golf and being able to hit it straight towards the hole. Even though Gabriel had a longer drive, he's still ending up further away than Maria that drove short but straight. Okay, that concludes our notes today on similarity and right triangles. Please bring any questions you have to our office hours.